Cardano's formula for solving a cubic, you know the first task is to depress it or get rid of the squared variable term. This involves a lot of binomial expansion that can be very tedious and time consuming. Fortunately, there's a faster method that doesn't require binomial expansion that I would like to demonstrate. I'm assuming you know how to take the first derivative of a polynomial. Also, this video won't involve Cardano's formula further after depressing the cubic. There's a lot of videos on that if you wish to look them up. I'm making this video because I couldn't find any others that specifically give this calculus shortcut and also include why it works. I'm going to start by demonstrating the regular method for depressing a cubic and then contrast that with the shortcut method, and then after that I'll do a proof of why it works. So if we have a cubic here, the first thing that that I like to do is get rid of this term here if we can. And I was nice to myself. I made sure everything was divisible by 2. So this is what we get. And so this is what we're going to work with. So we need to depress this cubic, and if you're watching this, you probably already know that we have to do a shift by negative b over 3a. Just like with a quadratic, negative b over 2a gives us the x part of the x component of the vertex. This thing actually gives us the x part of the inflection point, but I'm not going to go into that. Well, if you figure out what this is, in this case, we're going to get 5. So we're going to have to do a shift of 5. So we basically need to, we're going to make a substitution. X is going to equal y plus 5. And then when we're done, we're going to have to back substitute, and that's going to involve the fact that y is going to equal x minus 5. So these are our substitutions. Okay, well, so we have to put y plus 5 everywhere. Okay, and this is where the tedious part begins. I'm not going to do all the work. I'm kind of shooting ahead where I have a bunch of individual terms that are going to look like this. But if you're watching this video, you know what a horrific amount of work it can be. Supposed to be a 4 there. Okay, and then of course the squared terms cancel, and we end up with this. And of course, you know the format. I'm sure that we're going to have, we want something like this. And so here's P and here's Q. Of course, now we have to shift it back by using this, and now everything's going to be x equals 5, or sorry, x minus 5. Okay, just checking everything here. All right, so this is our depressed cubic. Now let's do the same thing with the shortcut. So I've written the original function with the a divided off, of course, the leading coefficient, and then written it as a function. And what we're going to do is we're going to take the shift. So we always take our shift, negative b over 3a. We know that's 5. And what we're going to do is we're going to evaluate the function at 5. Then we're going to use the derivative. So when we evaluate the function at 5, which is actually going to give us q, then the derivative will give us p. So I just used synthetic division here. You can do it however you want. There we go, and that is actually q. Okay, well now we're going to take the first derivative, we're going to get p. So the first derivative, which is the only one we're going to use, you can depress quartics by going up to the second derivative and so on. Now we're going to evaluate this at, again, our shift. And I'm going to skip ahead where I just used synthetic division again, but I'm going to skip ahead where I already have it. And that gives us 6, and that is going to be p. So for the final depressed cubic, what we're going to do is we're going to put the shift in. We're going to put the back substitute back in as well. I know when I back substitute, it's going to be the opposite of the shift. So we're going to do x minus 5, and then I know that here is going to be my p, but I now know that's 6. And then I need q, and that's going to be negative 20. And we're done. And that is way easier to get to here than the first method. So why does it work? The proof is very straightforward and quick to show. So we know we want to get from this to this. I don't have the back shift reflected here. I don't care about that. Really, this is all about getting P and Q. That's the struggle of this whole thing. And so we know that we need to plug that in place of X everywhere. So I've done that. You can verify everything for yourself that I've done that correctly. And when you get all these like terms combined and whatnot, then you're going to end up with this, and this is P, and this is Q. So if we contrast the other method where you basically take the shift and you evaluate the shift at you evaluate the function at the shift, you get this, and it's the same exact thing as this. So this is Q. And then when you do the derivative and evaluate it at the shift, you're going to get this, which is exactly the same thing as this. And so there you can see that this will always work.